Très bien, je vous propose de démarrer. Merci à tous d'être venus si nombreux à ce 31e Performance User Group. Le prochain, ça sera le 3e anniversaire. Donc il y aura une petite surprise avec le pot. Mais pour l'instant, on va parler du talk d'aujourd'hui. Latency from dream to nightmare in 100 milliseconds. Adam is coming to speak about that. He's DevOps at Algolia, a search engine on internet, and he will explain it a lot better than me and with a lot better English, I'm sure. Un petit message d'Octo qui nous accueille tous les jours. N'oubliez pas que nous recrutons, nous avons des missions sur ces sujets-là, sur beaucoup d'autres sujets en lien avec DevOps, la performance et l'architecture. Donc si ça vous intéresse, n'hésitez pas à venir me voir, à venir voir Borémy, qu'on ne voit pas beaucoup, mais qui est au fond de la salle tout le temps. On pourra vous parler d'Octo. Encore un peu de pub pour Borémy qui est au fond de la salle pour s'occuper de la vidéo. Qui nous permet de mettre en ligne la plupart des sessions du PerfUG. Donc je vous ai mis la copie d'écran. Vous allez sur perfug.github.io. Vous avez un onglet compte rendu et dans compte rendu vous avez une image qui va vous envoyer sur le lien du service qui héberge nos vidéos. Et vous aurez la vidéo jusqu'à la dernière session au mois de mars, c'est ça Borémy? Donc toutes les sessions sont à jour. N'hésitez pas à les consulter d'anciennes sessions, à les recommander à d'autres personnes. C'est là pour être utilisé. Prochain PerfUG le 19 mai, 3e anniversaire. Donc je vous donne rendez-vous dans un peu moins d'un mois et je vais laisser Adam prendre la parole. Merci.
Oh, yeah, okay. Yeah, fine. Okay, okay. Well, I lost my picture, so we should get... No? Get it? Should I hold it? Okay, cool. So do you hear me? Does the mic work? Okay, do you hear? Yeah, okay. Seems cool. All right, cool. So welcome everyone, and thank you for this opportunity to tell you something about my daily struggle at Algolia. At Algolia, I work as a DevOps and a security engineer, and my responsibility is the infrastructure that powers the search engine of Algolia. Who is not familiar with what Algolia does, or anyone, can you just raise your hand so I have just some idea to talk? Okay, so Algolia is a search engine. We provide a search as a service. It's an API. And you push us data, and we provide you an API to search on top of the data. So that has a lot of constraints, and I will later on explain why we care so much about latency and why 100 milliseconds for us is a nightmare. Okay, let's start. So when you have your infrastructure, you have your servers, you have your service, normally you host it in a single data center. And the longest distance that you actually see inside your service is something between a rack. And from a rack to a different rack. you definitely try to host your servers inside the data center very dispersed, in a very sparse environment, so you split your failure zones. You are in different racks with the different power supplies, with the different network switches in different network segments, so if one of them goes down, nothing really happens. But okay, you still need your services to communicate. And with microservices, it becomes even a bigger issue because you have a huge fan-out of requests in the backend. So you have a pretty heavy communication. But inside the data center, the thing that you can expect normally is 1 millisecond latency. That's kind of the top that you should expect. Normally, you will get something to 0.1, 0.5, 0.8. But going above 1, that's pretty far. 1 millisecond with the speed of light is approximately 300 kilometers. Inside the data center probably is not 300 kilometers wide, so you should not get over that. But what if we talk about internet? So let's take an example that you are transferring something from New York to Paris. So let's consider a US East, someone deploying something to AWS, mostly zone or region US East 1, that's in an Ashburn area close to DC. So it's in the West Coast, in the East Coast, sorry, and communicating from Paris. So very typical, a lot of services are deployed in US East. What is the latency that you can expect? Okay, simple physics, the distance divided by the speed of light is 39 milliseconds, and that's cool, that would be fine. The reality is that the distance between these two locations in a practical sense is 85 milliseconds. So you cannot just make the simple mathematics. There are a lot of devices in between, a lot of services in between, which are slowing things down. And your original expectations are more than twice. And you somehow have to deal with this. And this thing can change. It's a cool one. If we take two arbitrary spots on our small planet Earth, purely from the physics point of view, the maximum latency that you should experience is 133 milliseconds, which, let's say, for most of the applications would be okay. But if we take an example of going from Paris to Sydney, you are on more than 300 milliseconds. Why? There are a lot of issues in between, a lot of devices relaying, they have some delay, fibers are not going the shortest path, it's not as the plane flights. So you have to count with this. And the reason why this applied largely to Algolia is because what we do, we say, inside our engineering team, we say milliseconds matter. And for many services, milliseconds don't matter. For us, milliseconds matter. And the reason is that we provide search, and search as you type. You type a character, you get a response. The longer it takes, the bigger the impact is on the business. People don't want to wait. And the faster it is, the faster the happier the users are, and the faster they find what they are looking for. So raising by 100 milliseconds, raising by a latency of 100 milliseconds has been proven by Amazon on doing a trial, cost them 1% of revenue. That can be a big thing. And it's 100 milliseconds. And you see, between Paris and Sydney, you should have 133, you have 300, okay. That's 200 milliseconds extra. We are talking about 2% of revenue. No one cares. And the thing is that inside Algolia, when we deploy our infrastructure, we always replicate data 3 times. And we deploy them on 3 independent servers. And in the locations that need very high resiliency, we deploy them in 3 different data centers. So actually, the issues that you don't see inside the data center, we see, because we consider the region to be a data center, although it contains 3 separate data centers with 3 different, not even availability zones. We are talking about 3 completely different providers that connect with them on a totally weird rules and unexpected results. But this is kind of the normal scenario which we can expect. So let's say US East, we have 3 data centers, and you see that even the latency on every single one of the links is different. But it's okay. It's still somehow around 1 millisecond. That's something that you can deal with. But due to our infrastructure, which is spread around the world, the scenario in most of the cases looks like this. And we have a primary cluster that has a very short latency inside a single region. And then we are communicating in a master-slave fashion to our slaves spread all around the world. And this latency can range from everything from 70 milliseconds to more than 240 milliseconds when the distance is, it's really a huge distance. So we have to monitor this. And every single latency spike affects us. We cannot replicate the jobs. The users in Australia will be searching on top of all data in comparison to the users in US or in Europe. And every single thing affects us. The interesting thing is that this is the same thing which affects most of the websites. Just no one really measures that, and no one realized it. So something like to give you a perception of at what scale we are talking about. So as I said, we replicate the data 3 times across 15 regions, inside more than 35 data centers. We monitor at every single point in time, we monitor more than 1,900 network links between servers. And that's inside the cluster, from the cluster to the slaves. Sometimes the slaves have to communicate together. And you can have per user individual configurations of cluster and slave relationships. And we need to be sure that it works. And if the network breaks, we need to know. All of that operates on more than 400 servers spread around the world, doing more than 12 billion search queries per month. And we have to be sure that the queries are delivered, the results are delivered as quickly as possible. And when there is an issue, we mitigate the issue and we don't impact our customers. Because 100 milliseconds for us is a lot. So something briefly about the internet. Internet is a very special place. Internet doesn't optimize for latency. Internet doesn't care about latency. Internet doesn't care about geography, and Internet loves airports. So, something about latency. When the Internet is developed, a new fiber is being laid down or new paths are being optimized, it's always in consideration of what traffic is going to be transported. But the majority of the traffic today that is being transported is video, which is not really that latency sensitive. You are talking about bandwidth. You can buffer the video for a few seconds, but if you need to transport the latency sensitive traffic, the internet does not really care. So the internet optimizes for bandwidth. When you have your website and you want the latency, so you have your website located in France, but you have your customers all around the world, normally the first thing that you do is that you apply a CDN. You cache your assets as close to the customer as possible so they load them quickly, and then the main web page is loaded slowly from the single point, but it's a single request, and by the time the customer is fetching the rest of it, it's kind of okay-ish. But you cannot do this for dynamic content. You cannot do this for an API. You cannot do this for a service where for every single request you expect a unique answer. And there exist actually many networks inside the, many networks at the world that are built for low latency, but you just don't see them, or you don't realize that you use them. One of the great examples are networks, are backbones built purely for stock trading, for high frequency, low latency stock trading. Those are networks which are built for the purpose of getting the lowest latency possible, because a millisecond might decide between you getting the deal or not. The other interesting example is Google. When you try to just ping google.com, you will discover that you are at like 2 milliseconds. But there is no data center in France of Google. You will get to some point, to the edge of the network of Google, that you will enter their network, and then it's in their best interest to the shortest way possible deliver you to the data center, process your request, and return you the result. And it's purely for them, for no one else. There are many ways how to do this. And then one very interesting example is Riot Games that actually started to build their low latency backbone in the US for running a League of Legends. Due to this simple reason that their users, the players, were expecting high latency when reaching their servers. And when you are playing a game that is latency sensitive, and suddenly you have a spike, okay, suddenly it might decide between you survive and you die. And that's a big thing. They started to buy fiber in US, started to build their own network, and starting to do something in a sort of what Google does, getting closer to their end users and then dealing with the transmission of the data to the data center the fastest way possible, because it's not doable over the classical internet. Another thing is, internet doesn't follow geography. Just because the two places have some shortest distance between themselves doesn't mean that the internet will follow. And I have one example to show you. Let's imagine that you want to transmit data between Paris and Singapore. That is almost 11,000 kilometers. And you are here in Paris. And I did the test. I did the test yesterday. And I did the test from our office here in Paris. And then I did the test from a server that I have hosted in a data center here in Paris. Same geographical location and the same destination. This is how it looks when I was going from Paris. One thing I forgot to mention, if you will have any question during my talk, don't hesitate to interrupt, because as the things will continue, and if you will not be able to follow, some things might be confusing. So if you have any question, if something is not clear, don't hesitate to ask. I will be glad to answer. This is how looks a trace route from our office in Paris to one of our servers in Singapore. So you see a step-by-step how the data is going across the world to Singapore. And here are highlighted some interesting points. First, you see something which appears as a PAR, TH2. PAR as Paris, and TH2 is a data center in Paris. And then we can see in a pretty clear way that we go Paris, Marseille, Mumbai, Chennai, and we are in Singapore. Seems okay. That's when you put into Google the shortest way from Paris to Singapore, it will offer you a flight from Paris to Singapore, and you will actually see it this way. This is how it looks. Paris, Marseille, Mumbai, Chennai, Singapore. 160 milliseconds? Okay, seems fair enough. Okay, what about from the data center? This was from the office. You know, like, people are kind of used to that the connection at home is pretty bad. Like, you have a DSL, or before something like the latency is jumping, sometimes not okay, but like a professional connection of a data center has to be better, because it's a data center. The data center is serving the customers from all around the world. It has to be better. So let's take a look how it looks when we go from a data center. And let's highlight some interesting points. The path is completely different. It still goes from Paris. The interesting thing is, I'm very convinced that actually my provider is hosting in the same TH2 data center. But we see something which is called AMSTNL. That's in Amsterdam, Netherlands. Then we continue, and at hop 6 we are at ASBN VA. That's in Ashburn, Virginia. We are at the east coast of the United States. And then we go to SNGP-SI, that's a Singapore. The city is named as the state, but and we arrived in Singapore. So how it looks? The same, right? Just before, we had 160 milliseconds. Suddenly we are at basically 260. And the 100 millisecond matter, and it matters a lot. We go from Paris, from the same geographical location. We are talking, okay, Paris is 100 square kilometers. It's not that big. It's 10 by 10. And we go to exactly the same server in Singapore. Yet, you might go to opposite hemispheres of the planet. And the last thing is airports in the internet. What you have seen before, the coding of the routers is, you can do it yourself. You can just make a trace route to any server, and you will always see some weird marking of the servers. They actually make sense. They have sort of a style. Every single provider has a style. They follow a certain guidelines. And sometimes from the name of the server, you can even discover like the manufacturer of the server, because it's written inside the domain name of the server. You can discover if it is multiple links bind it together, if it is a 10 gigabit link or a 100 gigabit link, or if it is a Cisco, or if it is a Juniper, and mainly where it is. And one of the most common marking of the servers is marking by the IATA codes. And those are the codes of the airport. So if you, for example, try to trace a website which is hosted by, or it's proxied by Cloudflare, you will see that it will say in the HTTP header, proxied by Cloudflare CDG, and then there will be an ID of the server. So Charles de Gaulle, you know that you are in Paris. And all of this. And this is a good thing to remember, because then when you are going through the trace route, something is going on and you are trying to debug, you will end up with 3-letter shortcuts, and if you remember the airport, you suddenly know where you are. If not, you can always find it, but some of them are obvious, like JFK. Okay, fine, people remember. Charles de Gaulle, okay, in France should be pretty obvious. But for example, Ashburn translates to IAD, but the Ashburn area around the Washington, D.C. is basically the heart of the internet nowadays as we know it. This is one of the most common ones. So out of this, what we know, I want to show you a couple examples of issues that we have seen in production, out of nothing, and we had to tell our provider or their provider that they have an issue because they provide an internet connection, but the monitoring is kind of like, nah, not really. Best effort. So our cluster in Japan is the 3 servers which I have shown at the beginning. Those 3 servers are spread between Tokyo and Osaka, just for the purpose that the data centers are geo-distributed, they are kind of resilient, and the link in between is provided by the provider of our server provider. So for us, from our point of view, they're hosted by the same provider, the same people are managing the servers. And on average, we see 8 milliseconds of latency in between these servers. From Tokyo to Osaka, okay, fair enough. This is the baseline that we have set. Suddenly, one day, we got an alert that and our threshold was 10 milliseconds inside the cluster. Then we knew that consensus inside our cluster is probably going to slow down or break. So we got an alert that the latency is higher than 10 milliseconds. It's a raise for more than 20% already from 8 milliseconds. In majority of our locations, we are talking about latency of 1 or 2 milliseconds. So 10 is pretty high. So we took a look, how much is that? And it was 110 milliseconds. So 110 milliseconds, let's say from the point of view of speed of light, we are talking about 30,000 kilometers. Osaka and Tokyo probably didn't move, so something happened. So again, let's take a look what happened. So we went to the server, and we took a look how the server is reaching from Osaka to Tokyo. And since we control the server, so we can take a look what is going on inside the network. And we went to the server in Osaka, and we took a look how it reaches Tokyo. And we saw that pretty quickly, it arrived to Tokyo over a 10 gigabit link. That seems fair enough. And then in Tokyo, it goes to the network of our provider, and that seems totally okay. There is something unknown. It's not me who removed that. It did not resolve the IP address to the domain name. But okay, there is a hope something happens, and then we end up in Tokyo. We are at 110 milliseconds from 8. Something is going on. All right. So you can take it vice versa. Every time you are debugging something in the network, you cannot take a look from one place. Every time you will be complaining to your provider that there is a latency issue, they will always, every single time, they will ask you for the same thing from both of the ends. Because it doesn't have to be the same. Internet is highly asymmetric. You might be going from Tokyo to Osaka and from Osaka to Tokyo around the world. And that will be okay, and they will tell you it's okay. That's like no one really minds. And they will always ask you to show them to you, to you show to them from both of the sides. So their network engineers can actually take a look and see where it is asymmetric and who is responsible for that. So we took a look at Tokyo to Osaka. It's like, okay, Tokyo, Los Angeles. Okay, doesn't work. Los Angeles. It's cool, it's a 10 gigabit Ethernet, it's 100 gigabit Ethernet inside Los Angeles, 10 gigabit again, and Osaka, and then it's okay. Then the increase of the latency is negligible. And then we arrived correctly on our server. That's weird, but this is what happened. The link in between Tokyo and Osaka was not managed by our provider. It was not their link. They were just using their internet provider. And they built 2 data centers, and they were using the same connectivity as for accessing the internet, just in between those 2 data centers. And since in Tokyo, the router decided that it doesn't know any way to Osaka, the best way how to send data from Tokyo to Osaka was via San Jose in the United States. But the ratio is not proportional. But you can imagine that you are going suddenly via a fiber that is going over the whole Pacific just to bounce back and return basically to the same location. So we send an email to our provider saying like, guys, this is like not okay. And they are like, really? Like, where is the issue? Please justify that it makes you an impact. Like, okay, what do you mean makes an impact? Like, you are bouncing our data halfway across the planet. Like, it makes an impact. Okay. First time I got contacted by a creative director of the company. He was not that creative because 6 hours after it was still not resolved. 6 hours after I got contacted by a senior network engineer, and it took 5 minutes and it got resolved. So when you have issues like this, always insist on escalating the issues to the network team. Don't let like support deal with that. They cannot. It requires some heavy reconfiguration. But basically what the guy did was that he changed the way that the data is being sent from one provider to a different one, and boom, issue was resolved. But none of them was monitoring this. They were not monitoring the latency in between their 2 data centers. They didn't care. Because their customers, majority of their customers were using their data center to access the internet or to provide a service. But those 2 data centers were not really communicating with each other. So if you end up with an application which will be spread across multiple data centers, as you should not rely on a single data center. You should also monitor what is the latency in between those data centers. Because not it might break, it will break. The last time I saw a break was 3 hours ago. So it will break again. And I got another example. And you think like, okay, it's in Japan, maybe the connectivity is not that good, so they're like, okay, US, West Coast of US. I say, okay. San Francisco, Silicon Valley, technological mecca, everything is perfect. No, it's not. It's actually pretty bad. So we have servers in, at that time we had servers in one data center in San Jose. Up till today, I'm still trying to figure out how they cool the data center because it's not easy. If you go there as a human, it's like it's horrible, but there is a data center. And our customer was having the backend in AWS, in Amazon Web Services, in the region US West 2, which is in Oregon. It's not really where you would like normally expect to be close to San Francisco or San Jose. It's really in Oregon. Precisely, it's in Boardman, or at least that's where they are hiring their data center technicians. Normally, when you look for locations of the data centers, it will not give you a map with like addresses. But if you go to the job page and you look like data center technician, Oregon, it will give you the name of the city where you are going to work. So probably you are not going to commute for a few hundred kilometers. And the traffic was always going via Seattle. It was fine. That's also a huge technological hub for Microsoft, Amazon, and then back to San Jose. The average latency was 21 milliseconds. The customer was fine with that. They were aware that they are bouncing across the whole West Coast. Okay, fine. Up till one moment when they said, like, guys, it's broken. Okay, it's not. But it really was. And they sent us a screenshot from their new relic, monitoring the latency to our service. And you can see that everything works until it doesn't. And that kind of broke their backend. They were not counting with such a huge latency. And we are really talking about something like really 21 or maybe 40 milliseconds with the round trip time, going up to 300. That's not okay. That's 270 milliseconds between those two areas. 27,000 kilometers. That's a lot. Something has happened. And it was really serious for them. And you can actually see on the timeline, by the time they managed to tell us, it took a lot of time, but luckily for them, they were monitoring it. And the interesting thing is when they started to push the data, it kind of recovered. So we were like, okay, that's like super weird. So we went to investigate, and we have discovered what happened. We have deployed a micro instance in AWS, US West 2, and we started to do the same thing between our servers and AWS and trying to figure out what was going on. And this is what was going on. The provider of AWS decided that from Seattle, actually it's going to send the data to Denver, and then from Denver, it's going to send the data to San Jose. Like this would not have been enough, the router decided that it's maybe not that bad thing to like drop 20% of the data. The reason the connection worked is that our API is based on TCP, and TCP, when it loses a packet, starts to retransmit. When you lose a 20%, okay, it's a pretty high chance to actually lose a packet, but the TCP can retransmit, it can lower the size of the packet and retransmit, so eventually the data gets through. But it takes a lot of time. That's actually why they don't see a timeout in their graph, but they see a high latency. Their operating system managed to push the data through at the cost of very high latency. And so we started to take a look, like Seattle, Denver, San Jose, okay, that looks okay. So we reached out to Amazon, and we are like, guys, you have issue. And they're like, no, we don't. So we're like, okay, fair enough. It's Amazon. You don't want to fight. So we reached out to our provider, and we are like, guys, you have issue. They're like, no, we don't. Like, okay. So we started to dig with them, and they said, like, okay, we have tried to switch the link on our side. It stays the same. Like, okay, that's fair enough. That's enough ammunition to reach back to Amazon. It's like, guys, the issue is not in your network. Okay, I'm repeating, is not in your network. It's right in front of your network. And please contact your provider to fix that. And they are like, it's not in our network. We cannot fix that. It's like, yeah, that's what I said. It's like, please contact your, no, you contact them. No, we are not their customer. You are their customer. Can you please contact your provider? And you kind of get this ping pong with Amazon support. But it's really cool. Like, if you have the endurance, always go for the live chat. The people are great. Like, actually, their people on their support on AWS are great. They can help you with so many things right on the support. And when they cannot, they will even call you. I spent one night with a guy on a phone, just like trying to debug stuff. Pretty cool. So we were like, okay, it's not going to get resolved anytime soon. So we came with a crazy idea to start proxying the traffic. Like something like Cloudflare does for your traffic to going to your website. We're like, hey, we can do the same thing. We have a new data center. And we were like, I don't know, like 2 days from putting it into production and actually spreading the cluster across multiple data centers. And this issue would have been resolved just by changing DNS records and shutting the servers down. So we're like, okay, we can deploy a proxy in the new data center and relay the traffic via a totally different data center with a totally different provider, with a totally different ISP, using a totally different routes. Well, the idea was great. So here are the AWS availability zones. There was our server, then there was the edge of of our provider's network, and then all the availability zones were going to a single router in Seattle. So it's cool. Multiple availability zones are cool until they go to a single router outside and the router breaks. So what we have tried with our customer was really great. They were like, okay, we have everything split between multiple availability zones. We can like load balance the traffic to a different one. Okay, try. It still does the same thing. Okay, try different one. It still does the same thing. They have tried every single availability zone, and every single one of them had packet loss of 20%. Like, what do you want to do? So at that moment, I was a bit desperate, and I was like, guys, you know, like the fastest solution probably would be, can you switch your backends to US East? And they're like, oh yeah, sure. Like, wow. How many of you can like take your data center and move it like to a different end of the continent, you know? But the guys were great. They were like, oh yeah, if it does it solve the issue? Oh yeah, sure. Okay, then we can do it. And the person I was talking to started to prepare a moving of their complete backend to a totally different region. Like, oh yeah, easy. Like, respect. So okay, we have deployed the proxy, and we have discovered that although our provider in a second data center uses a totally different ISP, it ends up at the same router in Seattle, and it gets the same packet loss. Like, okay, so we don't know what to do. The traffic was flowing through the proxy just in case that some of them makes a change and tries to fix it. One of them would recover. So one server was proxied, two of them were not. So at least 1/3 of the traffic could have a reasonable latency. No, didn't work. In the end, the next day the provider said, oh yes, we have an issue. We got email from Amazon, yes, the provider confirmed that they have issue and they are going to fix it. Okay, Eureka. So this is an issue which is very complicated. It's outside of your network. It's outside of the network of your destination. It's somewhere in between. Who is responsible? Who is supposed to contact who to resolve it? Because apparently no one has noticed. And you are the first one you are the first one at the fire, and you are like, okay, I want to solve this, but no one wants to talk to you. Like, talk to them. No, talk to them. It's not their issue. Like, oh, come on, guys. So we end up in, but okay, in the end it got resolved. The router got fixed. The connection improved. And in order to mitigate a lot of these issues, our provider actually was so great that they have deployed a private connection with Amazon on the West Coast, just to avoid any intermediate elements that could break. And if it breaks, suddenly we know it's their fault, and it will be easier to fix. So okay, that was West Coast. Now East Coast. Okay, that's the heart of the internet. That's great. It's like a super advanced area, like super connected. Everybody is connected to everyone. Like we are talking about tens of terabits of data like flowing, but like super weird issues. So we got servers in the Ashburn area because mainly the reason is in the Ashburn area in the East Coast, US East 1 region of AWS is located, and all the availability zones. This is the first region of AWS. This is the biggest region of AWS. This is where everything is hosted. This is where majority of the internet is located. This is where majority of the networks are located. So you want to be there. You want to be in the middle of everything. But at that time, we were already smarter, and we had two different providers. The cluster was spread, so even if one of them has issue, or if there is a route leak and suddenly network disappears, like Amazon did a few months before, everything is going to be okay. But when we deployed the cluster, and when we have deployed the second provider, we have noticed a bit of imbalance. One of the provider, when reaching Amazon, was at the maximum in 2 milliseconds. But the other one was at 8. Okay. The providers are located in the same location, going to the same point of Amazon where their network is ending, yet you have a factor of 4 in the latency, and that's a lot. So okay, the same pattern, the same investigation. From a data center to Amazon. Okay, fine. This is the IAD, remember, Ashburn? This is the Ashburn area. Everything is fine. Everything is fine. Everything is fine. Here you see a boundary when our provider gives it to a network provider of Amazon, so it switches to a different network. Also the naming switches. And you see the Ashburn, Virginia, okay, that's fine. And then trace route inside Amazon is always tricky, but okay. It arrives to destination. Okay, that seems fair. You are sending it from Ashburn, it arrives to Ashburn, that's fine. Okay, the other way around. From Amazon to the data center. Okay, that's inside Amazon, that's always a lot. And then you end up DCA, Washington, D.C. That's not completely Ashburn, that's a bit on the side. Washington, D.C., JFK. Boom, we are in New York. Then you continue New York, and you see this is one provider, and suddenly they give it to our provider in New York, and they put it back to DC, and to Ashburn, and to arrive to our servers. So this is what our two providers managed to create together. In order to send data inside Ashburn, they just like bounced it via New York. And that puts you in a very tricky situation. Because what you expect is Ashburn communication, super low latency, everybody has huge links, lot of capacity, but suddenly you are bouncing via New York, imposing you a 6 milliseconds of latency, and no one cares. So we reached out to both of them and we are like, guys, this is not okay. And we didn't expect this, but our provider said like, hey, it's AWS. And AWS said, hey, it's your provider. So we were like, okay, again, in the middle of both of them. And our provider was very convinced that the issue is not on their side. And AWS support was very convinced that the issue is not on their side. And it was escalated to the network teams and de-escalated because the network team said, oh, it's 6 milliseconds, we don't care. We pushed again, like it matters. Okay, escalated and de-escalated. Up till the moment when really, seriously, AWS asked, can you please provide explanation when 6 milliseconds makes a business impact? What? You are bouncing our data through New York and you are asking us, like, what do you mean business impact? Like, yes, it has a business impact. Can you please clarify for which application this makes a business impact, like ours? Why do you care? But it seems like their internal procedure was like, not that they cannot do it, they just need a reason for a customer to justify that they will spend the resources to fix this because it's okay. It's okay to send the data like this. And to make it more difficult, between Amazon and our provider were two different providers. So when our provider was sending it to them, it went via a different network. It went okay. Our provider was sending it to Amazon from Ashburn to Ashburn. Just when the traffic was going back, it went via New York. And that's actually greatly visible in here. You see that everything is in Ashburn, and that's okay. That's still the provider of Amazon in Ashburn, and everything is still fine. The latency is 0.3 milliseconds. That's fine. But suddenly, when the traffic appears inside the Amazon's network, boom, you jump to 8. So on the way there, it's okay. And on the way back, it takes a round trip via New York. And you only see it when you take a look from the other side. So we started to negotiate with them. We started to provide more and more information. And it took me 8 months to fix this. 8 months ping pong with both of them, with their support, trying to explain them it really has this business impact. It seems like one of the guys in Amazon actually got fired because someone else took over the ticket, and he was like, can you please again provide a reason why it has a business impact? Like, okay, I will reference you the old ticket, and then again and again and again. And as it turned out, the configuration was actually on the Amazon side. Their network engineers decided to send it via New York. And one of the things is, I'm not sure how far you are familiar with how routing inside the internet works, but basically the networks are in a sort of mutual agreement relation. But it doesn't have to be symmetric. You can say, hey, I'm willing to send you data. It's like, okay, fair enough. And unless the other side says, hey, I'm willing to send you like data from my network, it's not symmetric. And inside the graph of the relations, our network was propagated in the network of Amazon. In both of them, actually. But they said it's not. And you know, they say, we don't see it. And you're like, it's there. No, but we don't see it. There is a cool thing, which majority of the really large network providers around the world provide, and it's called Looking Glass. And they give you a tool that allows you to take a look into their routers. You can choose a location. Sometimes you can choose like a very specific router. And if you understand what is going inside, they will give you the option to almost dump the config and take a look what is going on. What routes they see, from where, who is announcing them. Are they changing some priority on a local site? So when Amazon said, we don't see it because our provider doesn't give it to us, we were like, okay, that's not true. Because the looking glass of your provider says our network is perfectly visible and you can send us the traffic, just you don't want to. And so really, 8 months of ping pong, and it has been a month ago when it finally changed. This is from our monitoring system, monitoring the latency from Amazon to our cluster in US East. There are 2 lines, a blue one and a red one, which are pretty much the same because the servers are in the same data center. And then this third one is in a different data center, and it was way higher up till they fixed it, and right now it's even faster than the other one. So don't give up. Don't give up, really. You can win. It's okay. Just have to be really persuasive, and you really have to give a lot of information. If you have this issue and you don't know what to do with it, reach out to someone who has some network experience, speaks the language of the people, because sometimes they just don't want to talk to you. It happened to me today. Basically, I have discovered the identical thing, just with different pairs of providers. Right now, in US East, we have 3 different providers. So the number of issues kind of like grows exponentially. And I have discovered identical issue. I send them an email to a support and I'm saying, guys, like, you are bouncing the traffic via New York, it's not okay. This provider is sending it to you correctly, and you are not. And they're like, okay, so let me explain you how routing in the internet works. You know, there is a mutual agreement, blah, blah, blah. And then you have like a paragraph where the guy is explaining to you how routing in the internet works. And then he says, we think that the latency is in the limits. Really? Like from Ashburn to Ashburn, 8 milliseconds. So it's like, thank you, I understand how the routing in the internet works. Can you please fix it? Yes, of course. Okay. So in the end, it didn't take 8 months, it took 2 hours. But I had to go through the teacher guy who was like, I will explain you why it's not possible, because it's just doable. Okay. The situation is not that desperate like normally. What you can do with that? How you can not really avoid it. Don't have dreams, you are not going to avoid it. It's going to happen again and again and again. What you can do? Some of the things that you can do is mainly for your application and whatever you host. Even if you have a web page and you are just having customers, even in France, this is still super useful. You should definitely have an independent monitoring of the network. Your customers will be coming from multiple networks. You are going to be calling external services. Are you monitoring the latency to external services? Are you monitoring the latency to your customers, from your customers? What is the reachability of your application? All these things that you can monitor. And you can go for a simple solutions like ping them. You can just ping your site from multiple locations once in a while, and it gives you sort of an overview of your availability from all around the world. Not from everywhere at the same time. They always do it like from one place, and the other one, and then the other one. And then when your site breaks, it slowly goes red, the whole planet, but not at the same time. Or, if you want to go really deeper, the one thing which I have no words for, I don't know how to recommend this 1,000 eyes. Take a look at the service. It will give you an incredibly detailed overview of the performance of your service. It will tell you how long the page is loading, how long the DNS resolution takes, how long it takes to establish the SSL connection, how long it takes to make the TCP three-way handshake to your service. It will tell you if there is an issue from a particular location. And as I have shown you the very ugly trace routes from a command line, they will give you a very nice graphs that will explain you how it looks. And you will be able to go through it, through the routers, and what I have shown you, 10 gigs links and 100 gigs links, and they're going to parse all of this for you, and they will give you a very nice overview, and they will say, hey, it's a Juniper, it's a 100 gig link, this is the provider, this is the city, and you can go through it, and you know what's going on. It's incredible service. It's incredible service. It's definitely worth it. And it gives you just a wonderful overview, including alerts, including all of this. That's for more like ongoing monitoring, a continuous monitoring of your service. Then there's another thing, and that's very interesting, a TurboBytes Pulse. It's more like it's a project of TurboBytes that provides multiple CDN networks. And you can put there a domain name or an IP address, and they have a network of probes around the world. And you can actually host one of them at your home. That's what they want. That's the idea. It tests the latency from the end users. I have one at home. And you put there your website or an IP address of a server that you want to test, and they send the request to all of those small boxes, and they make a trace route and ping to your server, to the destination that you want. And then they give you an output. So in about a minute or two, right now, I think that they have 76 probes around the world. So from 76 places, a lot of them inside China. Like if you have customers in China, it's very difficult to test. So they have probes inside China that can very well test services inside China. Will give you a result, and you can analyze it. It will look like the trace routes that I have shown to you. It's a bit more parsed, but still, you will have an overview how your service responds. Mainly, if you are serving as a service for customers in Europe, they have a lot of probes around Europe, and you can test from France, Spain, Germany, Nordic countries, Eastern Europe, and you will see what your customers can expect. Because sometimes it happens, the customer says, hey, your website is slow. It's quick for me. I'm sitting in Paris on a gigabit line, everything is fine for me. The person might be on a DSL or a mobile connection somewhere in the middle of nowhere, and it says, okay, it's slow. Yes, of course. It's kind of expected. Once we get a customer and he says, like, hey, your API is broken. I'm like, yeah, probably not, but our monitoring doesn't say anything, but okay, we are willing to improve it. Can you please send us a trace route to our API? And on the first hop, it was 3 seconds. And then it continued. We're like, okay, are you on a mobile phone? And they're like, yeah, I have my edge connection and your API is broken. Yeah, maybe like your internet is broken, or like your connectivity is broken. It doesn't really, and nothing goes through. But you will have customers like this. And they don't care, like, where is your data center, how you do stuff, and they are far or their connection is bad. You will be the one responsible, and they will point to you, like, solve it. So you should be aware that even your provider, when you are choosing a provider, be very careful. You have seen that just going from Paris, from an office, and from a data center gives you totally two completely different results. And actually, the one from the data center is way worse. Be very careful when you are choosing provider. Today, when we are choosing provider, we always tell them, can you give us a one VPS, the tiniest VPS that you can do? And then we launch all of these services on them. And we analyze the data. And boom, we discover, oh, we have this great connectivity. And no, you don't. You are saying, oh, like Latin America, perfect for this. Oh, we have this like gigabit link to everywhere. No, you don't, because all your traffic goes via Dallas, and it doesn't really work. You are accessing Sao Paulo from Argentina via Dallas. Normal. DDoS protection. Yes, of course, because nothing goes through. So, and it can happen, and you will not know. And you need to figure out somehow. So invest into that. It's really cool. The last thing, what you can do is always the one which is the most difficult. It's to make your own custom monitoring. I don't recommend. It's super painful. It takes a lot of time. It costs a lot of money. And you need to have a really very specific use case. In our case, the reason is that we have many endpoints of our API. We don't have a paris.fr. You are not accessing our service via a single domain or a single set of even like 20 load balancers. No, we have 400 endpoints. And some of the pricings of these services don't really count with this scenario. So in your case, if you have a website and you are providing a service, you are basically monitoring a single endpoint from their point of view, and it might be really cool for you to have this overview. So we have built our own network, and every single one of these green dots is a server around the world. It's not a rocket science, it's a tiny VPS, which is running a small Ruby script, checking our infrastructure and sending the data to US East, to the heart of the internet, where everything is being processed and our monitoring is displayed. And in the end, it's interesting. And today, we are collecting more than 1.6 thousand different metrics just about our DNS providers. Like, are we monitoring your DNS provider? Do you know when they have issues? Because if your DNS provider doesn't work, your customer cannot access your service. No matter how super reliable your backend is. If your DNS provider misses the DNS request, boom, no one is coming to your website. So we monitor this. We monitor our API. So with the 400 servers, we have 46 locations of the probes around the world. That generates more than 3,000 metrics. And then we also monitor the latency of the network from 46 locations to all of our servers around the world in a 4-second interval. And we collect 73,000 metrics from this. Just to know that when our customer comes and says, hey, I have issue from AWS US West 1, we go to our US West 1 probe and we take a look, oh yeah, the probe also has issue. So it's not just you, it's the area, and then we can try to find something. The customer says, hey, we have issue, we have a probe in the area, and the probe sees nothing. Probably the issue is somewhere else. So with this, we generate a status page, which is normally status pages of services are like highly manual. Something happens, and you page someone, hey, can you please put on status page that something is going on? We were like, okay, we are not that many to do this. So we made the status page, unfortunately, automatic. So when something breaks, it is there before we manage to get paged. We get actually paged after it is on the status page. So even if you are lazy and you are like, oh yeah, okay, it's not that big issue, no, everybody sees. It's actually pretty cool. You can take a look. We are collecting a lot of data, and we are displaying them in a very unusual way. It's not really typical for status pages of services. There is this very common meme, like, have you ever seen a status page of a no-name cloud provider? They have 3 statuses. Officially, they have 4. They have green with a tiny eye icon. Then they have orange and a red one. Basically, no one has ever seen the red one. The green one means it works. The green one with the tiny little eye means it's broken. And the orange one is broken and the customers noticed. And like everything is on fire. And you open the status page and it's cool. It's like, everything is green. What is this eye? Oh, an elevated error rate. Oh, okay. Yeah, that's why my service doesn't work, because you have an elevated error rate. But yes, you can also do it like this. But this is one way how to do it. You can monitor latency in an active way. You can probe your service. What about monitoring latency in a passive way? Would it be doable? And this idea came to me on top of a beer with one of my friends. And we were like, hey, could you monitor a latency without monitoring the latency? because it's super annoying to run all these probes. They're like pinging your service, it consumes resources, and it's like, yeah, and if, could we just like, and we cannot be anywhere. We cannot be everywhere. Like, we have customers with different connections coming from mobile devices, from everywhere around the world, and you just cannot have a probe everywhere. Could you just like get the information somehow? And then we were going inside our applications, and basically we imagined the stack of the application going from the application to the hardware layer and going down and trying to figure out if we can find a way how to get the latency in a passive way. And we came with the idea. When your client, are you aware of a three-way handshake of a TCP? When you want to open a TCP connection, you need to communicate with the server, agree on the sequence numbers, and only then you can communicate. And it's actually an interesting instrument because at the first, you send the client sends the sync packet to the server responds with the SYN and acknowledgement, and then the client responds with acknowledgement. So actually the server can somehow like determine what is the latency. Because the processing time of this should be 0, 0, nothing. It shouldn't really project in the latency, and most probably we will count this time in nanoseconds, not really even milliseconds, so in the millisecond resolution it will not be visible. So the server should be like, yeah, like, I can determine. And then we started with the crazy idea how we are going to make a network sniffer that will track the packets and it will calculate the latency and give us the round trip time for every single request. Because if you think about it, if you could implement this, you can get the latency of every single client accessing your service anytime from anywhere, always. And you don't have to do anything. Your server already knows everything. Well, as it turned out, this thing, someone was faster than me. This thing got invented in 2001. But it was cool. It was like we were just on top of a beer, and then I came home, and I was still able to browse the web, and I was looking for this information, and I was like, oh, it's doable. Like, someone thought about it. That's cool. It's not totally stupid idea. And it's called TCP info. Actually, Linux kernel keeps, sorry for Windows and Solaris and AIX people, I don't know how you can do it there. I can help you with Linux. I cannot help you with the Unix systems and Windows and whatnot. A Linux socket has this TCP info thing. And you can actually get these values out of it. And maybe some of you recognize, this is actually a configuration of Nginx. You can get it in your Nginx logs. Right now, you are monitoring who is coming from where, IP address, timestamp, what is the request, maybe what is the encryption. If you are like really picky and you want to see that your customers are using a TLS 1.2 and they're like really on the edge. But you can also monitor the latency. And you can get it like zero cost, just get the latency in the log. So you can give a round trip time variation, send window, receive window, all of that. And suddenly, in your log, you can have a latency for every single request. Doing nothing. Then it's just up to you to analyze the data, to alert on that, like any other log file. But if you are already collecting logs, most probably, and I hope for you, you are processing the logs somehow, and you are analyzing them somehow. It is very interesting. You can get some very interesting information out of that. Maybe about analysis of a latency sometime later. So if you're running Nginx, definitely consider putting this to your log, because suddenly you see that when customer says, hey, I have an issue, can you please tell me your IP address? Oh yeah, I see that you have an issue. I see that your latency jumped. No monitoring, nothing. You already have everything. It exists in Apache, but I have found it only in the Apache traffic server. There it's called a TCP info plugin, surprisingly. And you can just plug it in and Apache will learn from that. So, thank you for your attention. And if you have any questions, I will be glad to answer them. yeah, if you ask a question in French, you can. I hope Timbo is going to translate it for me. My French is super bad, so sorry for that. Or in Czech, I can handle Polish or Slovak or no. Okay, if you want to ask a question, I'm going to stay. So on top of a beer, no record, no microphone, no intimidation. We know how it works. All right.